Alrighty, today we're going to be tackling the intermediate values theorem, which is crucial for understanding the fundamentals of continuity and limits in functions. And luckily for us, this one is actually not too difficult to understand. In fact, I'd go so far as to say it's one of, if not the most intuitive theorems in all of mathematics. And if you don't take my word for it, well, let's just get right into it and you'll see. So to get us started, let's just say we have some arbitrary function f of x. And we don't know what the equation for this function is. But what we do know is that at the very beginning of the function, this function is going to be equal to 1. And at the very end of the function, it's going to be equal to 6. And then we can go from there. So let's just go ahead and put some arbitrary points. So we say that it starts at x is equal to 0 being equal to 1. And we can say x is equal to 5, for example, is equal to 6. So we have the start point and we have the end points. So what we can say about this is that if this is a continuous function, then, for example, like this, well, it's going to traverse every value from 1 to 6. And we can observe exactly that through some simple observation. So when y is equal to 4, for instance, we can go ahead and see that at this point here, it appears to be equal to about 4. And for y is equal to 3, well, we can see that there's a point here on our function that's going to be equal to 3. So it's going to traverse every value. All right, that's interesting, but let's go ahead and take a step back here. Why don't we try seeing if we can't construct a continuous function that does not fulfill the intermediate values theorem? So maybe we can make one that's a little bit more unorthodox, but, well, ultimately we have to approach 6 because that's defined as part of our function here. And, well, from what I'm seeing, there's no possible way that we could get up to 6 without traversing all of these numbers. So that means that it is going to be true for this function, and it's going to be true for any other function that we try. So we can try something like this, or some oscillating function like this. Ultimately, it's going to reach 6, and it's going to traverse all of these values. Now, it might traverse some other values down here. We can't say that for sure, but what we do know is that it traverses all values from 1 to 6. And if I sound like a broken record, then, well, I'm sorry, but I'm just really wanting to hammer this in. Alright, great, fantastic even, but how exactly is this useful? Well, let's say I asked you if there is some value f of x, so for some x value c, that is going to be equal to 4.18, for example, with nothing but the information that this function is continuous and that travels from 1 to 6. Well, yes, actually we can, because of the intermediate values theorem. We know that's going to traverse every value from 1 to 6. We know that traverses 3, it traverses 4, 5, everything in between 1 and 6. Which means that we can actually say that this does exist. There is going to be some value of c that is equal to 4.18. And there could be multiple, since again, we don't know what the precise shape is. So it could very easily be something like an oscillating function that gives us multiple potential values. But what we do know is that there is at least one point that is going to be equal to 4.18. So awesome, beautiful. All right, so we attempted to draw a continuous function that does not adhere to the intermediate values theorem. And unfortunately for me, considering as how this is a centuries-old theorem, that didn't go so well. So it seems like we're going to need to venture into a different realm of functions in order to do that. So let's try a discontinuous function now that doesn't adhere to the IVT. So if we were to try that, well, there are actually many different ways that we can go ahead and break this. So we can draw a function to here, and then we can have a jump discontinuity, and voila, we reach 6. But as you can clearly see, there are many values here that we just didn't touch whatsoever. And likewise, since this function doesn't traverse all values of y, that means that for some arbitrary value, so 5 for example, we can't say that there's going to be some sort of x value c that gives us that value. So for this function, as we've drawn it here, there is no value that gives us 5. That just doesn't exist. We can see that for some sort of value c, there is a 3. Just looking at this visually, you can see that there's one here and one here. But remember, we don't know what the shape of this function is. So we can't actually guarantee this. So we can't apply the intermediate values theorem to a discontinuous function. There are all kinds of discontinuities that could be present that just invalidate it. Alright, so the intermediate values theorem tells us that f of x is going to traverse all values within these two boundaries. Okay, brilliant. But now it's time to generalize it. So instead of thinking about this in terms of specifically 1 and 6, let's think about this in terms of a and b. So we have the variables a and b. So we have a correlating to an x value and b correlating to a later x value. And for the values of the function that make up our bounds, we have f of a and f of b. So in more mathematically rigorous terms, what we're saying is that f of x will take on all values on the open interval of f of a to f of b. And then we can analyze this in turn to say that some value between f of b and f of a, f of c, is going to correlate to at least one value, one x value of c that will yield that y value on this interval. Alrighty, so if we were to go ahead and visualize this, then if we were to just create a theoretical function like this, for example, then that means that we can say that f of c is equal to 4, for instance. And so that gives us f of c. You've seen this before. And then we can go ahead and just look at this visually and see that it appears to be equal to about 3.5 here. So c is 3.5. And this is only a theoretical function, but hopefully this gives you some idea of what these values actually mean, all these variables jumbled around, so you don't get too overwhelmed. Alrighty, let's go ahead and test some of our knowledge. So we have a pair of questions here. We should probably start with one. So if f of x is equal to x squared plus 5x plus 4, is the intermediate value theorem IVD valid? Well, in this particular instance, yes, it is, because this is a simple polynomial. We're not dividing by x or anything. We have no x terms in the denominator, which means that we're not going to have any undefined behavior like 0 over 0 or vertical asymptotes. So we don't need to worry about all that. So this is going to be valid for the IVD for all real numbers. So voila. And then number 2 here, we have what about f of x is equal to x squared over x plus 1? Now here things get a little more complicated because as we can see at this graph here, we do have a vertical asymptote at x is equal to -1. And if we go ahead and try that, that's going to get us x squared, which is 1 over 0. That does give us a vertical asymptote, just as we observe on this graph. So this is not going to be valid for the IVT. Now the story is not quite over for our intrepid function here, because we have a second part of this question. So if not, is f of x valid for the IVT on the interval x is greater than -1? And looking at this, we can see that the vertical asymptote is specifically on x is equal to -1. When x is greater than -1, well, this is actually going to be a continuous function. And if a function is continuous, as we can recall, the IVT is going to apply. And the reason for that is because it's going to be valid for all of these. It's going to traverse all of these values, and it's going to be a regular old function. So once we've gotten past the vertical asymptote, voila, there we go. Which means that, yes, it is going to be valid for the IVT on that specific interval. So just because the IVT doesn't apply to the entire interval of the function doesn't mean that it can't apply to certain components of it. Only if it's continuous, of course. Alrighty, folks, we're down to the home stretch. So we have one more component of the intermediate values theorem to mention, which would be roots. And roots are when a function f of x is equal to 0. And this is very commonly applied with polynomials, where you have 2 roots for a quadratic, for example, and the quadratic formula and all that. However, we can go ahead and use the logic of the intermediate value theorem to locate when we might see a root. So for this question, if f of -2 is equal to -2 and f of 0 is equal to 4, is there a root between x is equal to -2 and x is equal to 0? So what this is basically asking us is we have an x value of -2 and we have an x value of 0. And then those x values provide us with -2 and 4 respectively. But what's very important to go ahead and make note of here is that we have a sign change. So we have a -2 and a positive 4. And according to intermediate values theorem, we're going to traverse all values between these two. So that means we're going to go from -2 to -1 to 1, 3, all the way up to 4. But what's very, very important to note is that between -2 and 4, there is going to be a 0. That is guaranteed by the intermediate value theorem, which means that at some point between -2 and 4, or between the x values of -2 and 0, we're going to have a root, which means that between these two, there is going to be some x value that gives us 0. And just looking at this graph, we can go ahead and observe exactly this. So we start from y is equal to -2, and we go ahead and ascend all the way up to y is equal to 4, and it appears that we cross over the x-axis right here at x is equal to -1. Beautiful. Alrighty, that's all for today. Thank you sincerely for watching. I hope you enjoyed. If you did, very much appreciate it if you leave a like or subscribe, and hopefully I'll see you next time. So, have a wonderful day.